Hey, welcome. Today we're diving into the amazing world of light. And you know what? It turns out that a few super simple rules about how light bends can explain, well, pretty much everything, from weird optical illusions to the tech that's literally powering our world right now. Let's get into it. Okay, you've probably seen this a million times, right? You stick a pencil in a glass of water and boom, it looks like it's snapped in half right at the waterline. But why? What is actually happening there? And hey, it's not just the pencil trick. I mean, how can a tiny little dewdrop on a leaf suddenly act like a perfect magnifying glass, making the veins underneath look huge? It's something we see all the time, but it really does feel like a little bit of magic, doesn't it?
Well, here's the cool part. The answer to both of those questions, it's exactly the same. And no, it's not magic, it's physics. And I promise, once you get this one core idea, you are going to start seeing its effects absolutely everywhere. All right, so here's how we're going to break it all down. First, we'll solve that bent pencil illusion. Then we'll dig into the actual rules for bending light. After that, we'll see what happens when light gets trapped, which is super cool. And finally, we'll look at how we use all this stuff to build the lenses and mirrors that literally shape our world. Okay, let's do it. First up, let's finally crack the case of that broken-looking pencil. The big secret here has a name. It's called refraction. And what it means is this. When light from the bottom part of the pencil leaves the water and hits the air on its way to your eye, its path actually bends. The thing is, your brain doesn't know that. It just assumes light always travels in a straight line. So it traces that bent path back to the wrong spot, making it look like the pencil is broken. It's all an illusion.
But why does light bend in the first place? Well, it all comes down to one thing: speed. Light is the fastest thing there is, sure, but that's only in a total vacuum. The second it passes through stuff, like air or water or glass, it slows down. We measure how much it slows down using something called optical density. And here's a weird twist. Optical density is not the same as, regular density. Just look at oil and water. Oil floats on water, so it's less dense. But it's actually more optically dense, meaning it slows light down even more than water does. Wild, right?
Now, this bending isn't just happening randomly. Oh no, it follows a super precise and predictable set of rules. Rules that physicists have totally mastered. So let's take a look at how they can predict its every single move. So scientists have a number for this. It's called the refractive index, and we just use the letter N for short. Honestly, the easiest way to think about it is like a speed limit for light in that material. A vacuum has an N of exactly 1. Air is super close to that. Water, it's about 1.33. And a diamond, whoa, it's all the way up at 2.42. The higher that number, the harder that material slams on the brakes for light. And this all boils down to two simple golden rules. Rule number 1, when light goes from a less dense to a more dense material, so think air into water, it slows down and bends toward an imaginary line we call the normal. The normal is just a line that's perfectly perpendicular to the surface. Okay, rule number 2, when light goes from a more dense to a less dense material, like water back out into the air, it speeds up and bends away from the normal. And that right there, that's the bend that causes the pencil illusion. And this whole rule book, it's all wrapped up in one beautiful little equation called Snell's law. Now, don't worry, you don't have to memorize it. Just know that this is the powerhouse formula. It's what connects the speed limits, the refractive indices, with the actual angles of the light. It's the key that lets engineers design everything from your glasses to the giant telescopes that look out into space. Okay, so we just said that when light goes from water back to air, it speeds up and bends away from that normal line. So here's a thought. What happens if we keep increasing that angle? What if we push that rule to its absolute limit? I mean, really think about it. If it keeps bending further and further away from that line, is there a point where it bends so much it just can't get out? Could it get trapped in the water? The answer is yes, it absolutely can. Let's walk through this. At a small angle, light gets out, no problem. It just bends away a little. As we make that angle bigger, it bends more and more, until we hit this magic point called the critical angle. At that exact angle, the light ray just skims right along the surface at a perfect 90 degrees. But if we push it just one tiny bit further, that's it. The light can't escape. It hits the surface and acts like a perfect mirror, reflecting right back down into the water. This incredible effect is called total internal reflection. And this isn't just some weird physics trick.
This one single principle is behind some of the most amazing technology and natural wonders out there. You know the internet data that's bringing you this explainer right now? It's probably traveling as pulses of light literally trapped inside fiber optic cables, bouncing their way across the planet. That incredible sparkle you see in a diamond? That's light getting trapped and bouncing around inside before it finally escapes. Mirages on a hot road, rainbows, submarine periscopes, it's all powered by trapping light. Okay, so we've figured out the rules of how light bends. So what happens when we humans start building things specifically to control that bending? Well, that brings us to lenses. Basically, there are two main flavors. You've got your convex lens, which is thicker in the middle. Think of a classic magnifying glass. It takes parallel light rays and bends them inward, focusing them on a single point. Then you have the concave lens. It's the opposite, thinner in the middle, and it spreads light rays out, making them diverge. And just by combining these two types of lenses, we create the optical tools that have completely changed our world. A single convex lens, that's your magnifying glass. Put two of them together in just the right way, now you've got a powerful microscope. And that tiny, tiny camera on your phone, that uses a little convex lens to focus a real, but much smaller, image of the world right onto a digital sensor. Right, so lenses work by letting light pass through them. But what about the tools that bounce light back at us? Well, that, of course, brings us to mirrors. And just like with lenses, you've got two main kinds of curved mirrors. A concave mirror curves inward, kind of like the inside of a spoon. Get up close to one and it magnifies your reflection. That's why they're used for makeup mirrors or by your dentist. The other kind, a convex mirror, curves outward. It always makes things look smaller. And you see these everywhere, security mirrors in stores, and yeah, the side mirror on your car. Okay, but why on earth would you want a mirror that makes things look smaller? It seems counterintuitive, right? But the answer is super important. It's the field of vision. A convex mirror basically makes a trade. It sacrifices the size of the image to give you a way, way wider view of everything behind you. It's all about safety. And that's exactly why your passenger side mirror has that little warning, objects in mirror are closer than they appear. It's showing you a shrunken down image to help you see your blind spot. So there you have it. We started this whole journey with a simple, broken pencil and a glass of water, and we ended up with the super complex optics inside your phone and the safety mirrors on your car. And the amazing thing is, it's all of it, governed by the exact same simple rules of how light bends and bounces. So what are the big things to remember from all this? First, light bends, or refracts, for one simple reason. Its speed changes when it goes from one material to another. That's it. Second, if you bend that light at a steep enough angle, you can trap it completely, a phenomenon called total internal reflection, which is the secret sauce behind our internet. And finally, once we understood these rules, we started building lenses and mirrors to control light on purpose. And that's how we see everything from the impossibly small to the incredibly far away. You know, from the beautiful arc of a rainbow to the fiber optic cables that literally delivered this explainer to your screen, it all just starts with light bending in predictable ways. So the next time you see a straw that looks bent in your drink, or a flash of sparkle from a piece of glass, maybe you'll see the elegant physics that's really going on. My question for you is, what will you see differently now?